Section 20.8 Cooperative Magnetism. In solids, electron spins on neighboring transition metal centers may behave in a cooperative manner. And if we have a large domain of thousands of such transition metal centers, and the electron spins on these thousands of transition metal centers have the same spin, either same alpha spin or same beta spin, it's called ferromagnetism. Now again, let's imagine another large domain of thousands of transition metals of a different solid material. In this case, we find two neighboring transition metal centers have the opposite spins. So we have thousands of pairs of those alpha-beta couples. Alpha-beta, alpha-beta, alpha-beta. That's called anti-ferromagnetism. So now let's define this magnetic susceptibility, chi. It's a measure of how easy it is to align electron spins with the applied magnetic field. So if you put a material in an external magnetic field, this external magnetic field may induce a magnetic moment in this material. And this chi is the constant of proportionality. So this induced magnetic field is simply chi times the strength of the applied magnetic field. There are four different types of magnetic behaviors in this table: diamagnetism, paramagnetism, ferromagnetism, anti-ferromagnetism. So let's look at their values of chi. So copper solid, is a diamagnetic material because in copper there's no unpaired spins. So copper itself has a 4s1 3d10 electron configuration with one unpaired electron, but copper solid, all electrons are paired. And then we observe a negative value for copper. It's a very small negative value, 10 to the power negative 6, very small value. So the induced magnetic moment in copper is really small in a applied external magnetic field, and it's in the opposite direction. This behavior does not depend on temperature. And now let's look at paramagnetic material, such as this iron sulfate. It has a small value of chi. This is positive chi. So that means, well, if you apply an external magnetic field to this iron sulfate, there will be induced magnetic moments, very small, and also in parallel with the magnetic field. And then ferromagnetism, also positive. But if you compare the order of magnitude, so this is about 1 million times this one. One example is iron. So this is iron with a very large value of chi. Magnetic susceptibility. So that means if you apply an external magnetic field to metal iron, there's going to be a very strong induced magnetic field. All right, so that's why iron can be strongly attracted to an external magnetic field. And this chi decreases with temperature. This chi also decreases with temperature. And then finally, anti-ferromagnetism. Examples, there are many transition metal oxides that can behave as anti-ferromagnetic material at a low enough temperature. For example, manganese oxide, MnO, is anti-ferromagnetic at a temperature below 120 Kelvin. And there are some other transition metal oxides that can behave like a anti-ferromagnetic material at either higher temperature or a bit lower temperature. So at different temperatures, some different transition metal oxides have this anti-ferromagnetism behavior. And this chi increases with temperature at below a certain temperature. All right. So now let's look at paramagnetic. A paramagnetic has a positive susceptibility. A diamagnetic material has a very small negative susceptibility. I can give you another example of this paramagnetic material. It does not have to be a solid in this case. For example, liquid oxygen can be attracted by an external magnetic field because the applied magnetic field can induce a magnetic moment in liquid oxygen and actually in gaseous oxygen as well. Diamagnetic material. Well, I also can give you a few other examples in the liquid or gas phase. For example, liquid hydrogen, molecular hydrogen gas. They have diamagnetic behavior. All electrons are paired. So now let's look at this paramagnetic material. When the temperature goes up, the entropy increases. The electron spins are more disordered. And therefore, in this case, the chi value of a paramagnetic material decreases as the temperature increases. Right? So over here, variation of chi with temperature. When temperature increases, the paramagnetism decreases. Same for ferromagnetic materials. Below the Curie temperature, as the temperature increases, neighboring spins become aligned in a parallel manner. And then within a large domain of thousands of transition metal centers, they all have the same electron spin, and we have very large chi, and chi increases as the temperature decreases. Again, this is because as the temperature decreases, the alignment of those transition metals become more parallel to each other, more ordered. And that's why you're going to observe a more prominent cooperative matter within this large domain. And that's why chi increases dramatically. If you have an anti-ferromagnetic material below the so-called neo temperature, as the temperature decreases, again, you have all those transition metal centers aligned in a more orderly manner. But in this case, we have electron spins coupled with each other. So I want to show you the difference between ferromagnetic and anti-ferromagnetic. Ferromagnetic, when the temperature is low enough, all those transition metal centers are ordered, and the electron spins are pointing to the same direction. So within this large domain, we have a very large induced magnetic moment in a external magnetic field. This is anti-ferromagnetic behavior. So if you look at these two neighboring transition metal center, they have the opposite spins. Alpha beta, alpha beta, alpha beta, alpha beta, alpha beta, alpha beta. And then due to the coupling between the opposite spins on the neighboring transition metal centers, this domain behaves like an anti-ferromagnetic material with a really small magnetic susceptibility. All right. So again, when temperature decreases, you're going to look at a larger induced magnetic moment here, because all these are pointing in the same direction. Over here, when temperature decreases, again, it's going to be more ordered, but that means the electron spins are better cancelled. So in the ideal situation, you'll get just a zero overall spin, and that's why this chi decreases as temperature decreases in a anti-ferromagnetic material. So now here's the picture. If the temperature is high enough, all solid materials are paramagnetic. So this red line here, above this temperature, it's just paramagnetic. And the higher the temperature, the more disordered the transition metal centers, and also the more disordered the electron spins are. So overall, if you have a more disordered state, the electron spins tend to cancel each other. Then you have a smaller magnetic susceptibility. Only if the temperature is low enough, you can have all the transition metal centers being aligned in a more ordered manner, and then you will start to observe either ferromagnetic behavior or anti-ferromagnetic behavior. Again, it depends on whether all spins are pointing toward the same direction. That's ferromagnetic. Or you have pairs and pairs and pairs of alpha and beta spin, which cancel each other. Okay, so in this case, well, when temperature decreases, you get more ordered transition metal centers and more ordered alignment of the electron spins. But in that case, because a pair of alpha and beta electrons cancel each other's electron spin, you have lower and lower magnetic susceptibility. So that's why only when you have a low temperature that you can observe ferromagnetic behavior or anti-ferromagnetic behavior. All right? And if the temperature is high enough, you always observe paramagnetic behavior. And I'm assuming this material contains unpaired electrons, of course. If the material does not contain any unpaired electron, like solid copper, well, you will not be able to observe these three behaviors. You will just observe diamagnetism. All right. So now this T sub C is Curie temperature, and below T sub C of the material, you observe ferromagnetism. T sub N is the new temperature, named after new, and below this temperature, you'll be able to observe anti-ferromagnetism. So how can we observe this anti-ferromagnetism? Well, it often occurs through intervening ligands by a mechanism called super exchange. So right here, we have a ligand here. Now let me give you a more concrete example. Let's say this is a manganese transition metal center, Mn2+, another Mn2+. In between, there's a oxygen, oxidal ligand, bonded to both transition metal centers. All right, so within this oxygen, there's a p orbital with one alpha and one beta electron. They have the opposite spin, and then over here, this beta electron interacts with this alpha electron. So over here, you form a it's more like a covalent bond than a ionic bond. All right, and here's a bond. Here's another bond. Now let's look at the electron spins of these two neighboring manganese 2+ transition metal centers. Alpha, beta. We have a pair of electrons with the opposite spins. All right, and this is the so-called super exchange mechanism. And this is used to explain the anti-ferromagnetism behavior.